Good morning, all. Myself, Dr. Abhishek Tiwari. Today, I'm going to give a talk on stress strain curve and yield point phenomena. So, this is typical stress strain curve. So, when we have a tensile specimen and we apply a tensile load on the specimen, then as we apply load, the specimen elongates, and it can elongate elastically first and then plastically. So before I start stress strain curve, what is stress and what is strain? So stress is equal to force upon area, that is P upon A, and strain is equal to delta L upon L, that is equal to elongation in length divided by initial length. So as we increase load, there is increase in length, and the stress increases with strain linearly. And at point A, this is called proportionality limit. And from point O to A, it this stress increases with strain linearly. And from O to A, this is called linear region, and the point A is called proportionality limit. And in this region, it follows Hooke's law, that is sigma is equal to epsilon into capital E. So in this, sigma is strain, epsilon is strain, and capital E is Young's modulus. After point A, it further increases with strain, stress increases with the strain, but it is not a linear region. And after point B, we see yield point phenomenon. So point B is also called yield stress, and after that there is point C and D, that is called upper yield point and lower yield point, because an extra force is required for deformation to occur. I will explain the phenomena in the later slide. And so this C point is called upper yield point, and the D's point is called lower yield point. So because once we pass point C, we overcome the stress required for further deformation to occur, and then we can deform the tensile specimen with a lower stress. And after that, again, it deforms plastically, and from point D to E, it is undergoing strain hardening. So that means because we have sufficient strain now, and the sample is hardened due to strain, and we reach a point E, that is called ultimate strength. So ultimate stress, and also called ultimate strength. And this is the point. This ultimate stress is the maximum stress that an specimen can bear without failure. After point E, it further elongates at a lesser stress, and this from point E to F, there is necking. So that means the area in the middle decreases, and at point F, uh, it completely breaks through necking. So, so this curve in the black, this black continuous line, this is called engineering stress strain curve. And this in dotted, it is called true stress strain curve. So what is the difference between engineering stress strain curve and true stress strain curve? So engineering stress strain curve relates to when we have engineering stress, that is sigma is equal to P upon A, and epsilon is equal to delta L upon L, where delta L is final length minus initial length divided by initial length. However, for true stress, sigma true is equal to P upon A instantaneous, and so load divided by instantaneous area. As we can see here that from point D to F, there is a decrement in the area in the middle. So when we have P upon A, so area has decreased. That means we are operating at a higher load. So the true stress value will be higher than engineering stress value. Similarly, epsilon true, that is true strain, is equal to dl upon L, where dl is the change in length, change in length instantaneously for a infinitesimal increment, and epsilon is equal to dl upon L. So we can get a final deformation delta L with the integration of dl. Okay, so integration of dl we can calculate. So integration of dl we can calculate, and we can get the final elongation. Now, engineering stress strain curve is also called flow curve, and from point O to A, it is a linear region, and A to B, it is increasing, but it is not linearly increasing. But from point O to B, it is called elastic region. So what do we mean by elastic region? That up to point B, if we are loading and unloading, then it will come to its original position or original length. But after we have passed point B, there will be a permanent deformation in the sample. And if we unload it completely, still it will not reach its initial length. So this is typical stress strain curve. I have emphasized now on upper yield point and lower yield point phenomena. Here we can see that there is a fluctuation in the at the yield point, lower yield point, and there is also an elongation. So this is called yield point elongation, and this we define as yield point. So why this yield point phenomena occur? Basically, the yield point phenomena occurs in generally in low carbon steels. So when we have low carbon steel, carbon interstitial atoms goes down, goes below the positive S dislocation, and it locks the dislocation moment. So this upper yield point is due to locking of the dislocation moment due to carbon interstitial atom, which has now been set at the place below positive S dislocation. And once we apply load, and so the extra force is required to unlock that uh, dislocation pinning, and further, once it has overcome, it can deform at a lower yield point, and the elongation at the yield point is called yield elongation, and it is represented in this figure. Further, there is a formation of Luder's band in the at the upper yield point, and at upper yield point, a discrete band of deformed metal, often readily visible with the eye, appears at a stress concentration such as fillet, and coincident with the formation of the band, the load drops at the lower yield point. The band then propagates along the length of the specimen, causing the yield point elongation. In the usual case, several bands will form at several points of stress concentration, and these bands are generally at 45-degree. Here you can see these bands are formed at 45-degree. So these bands you can see that they are at 45-degree. So these are called Luder's band or Hartmann lines or stretcher strains. And these we can see with naked eye. We don't need like special techniques like optical or TEM to see these bands. So this deformation is also sometimes referred to as Pivot effect. When several Luder's bands are formed, the flow curve during yield point elongation will be irregular, each jog corresponding to the formation of new Luder band. After the Luder band have propagated to cover the entire length of the specimen, the flow will increase with the strain in usual manner, and this marks the end of yield point phenomenon. So here, this you can see at lower yield point, we have yield elongation. Now, this phenomena, yield point phenomena, is explained by quartal atmosphere. So, as I said in the slide, that this is the positive edge dislocation, and there is space below positive edge dislocation, and the carbon interstitial atom will sit below this and will lock the dislocation for further movement. So an extra force will be required for this dislocation to move and break this quartal atmosphere. So this is called quartal atmosphere around this carbon interstitial atom below the positive edge dislocation. Now strain aging. So let us say we have subjected one tensile test specimen, let's say low carbon steel specimen, and we have subjected it to deformation till point X. And so initially we have subjected it, we have applied load and it increased linearly, and then yield point has been observed, and this is lower yield point phenomena, and after that we have gone to point X. So we are discussing staging. So strain aging, and strain aging is a type of behavior usually associated with yield point phenomena in which strength of a metal is increased and the ductility is decreased on heating at a relatively low temperature after cold working. And this behavior is shown in this figure. So the specimen, if it is unloaded after point X and retested without any appreciable delay, without um, any wasting of time, then there will not be further yield point phenomena observed in this case. Since the dislocation have been torn away from the atmosphere of carbon and nitrogen. Now consider the specimen is strained to point Y. Now अभी हमने Y तक इसको डिफॉर्म किया है. Consider now that the specimen is strained to point Y and unloaded, and if it is reloaded after aging for several days, then uh, it is reloaded after several days at room temperature or several hours at an aging temperature like 400 Kelvin. The yield point will reappear. So if we have given sufficient time for carbon atoms to diffuse back to the place below positive S dislocation, then again there will be formation of quadral atmosphere and again there will be observance of yield point phenomena. The reappearance of the yield point is due to diffusion of carbon and nitrogen atoms to the dislocation during aging period to form new atmospheres of interstitials anchoring the dislocation. Now effect of temperature, or it's also called Portevin-Le effect. It's a French name. So we are going to discuss Portevin-Le effect in iron. So this is stress versus strain. So at room temperature, we have this normal behavior. But if we have heated the sample to 100 degrees centigrade, then actually there is a formation of these serrations. And this is because of the locking and unlocking of the quadral atmosphere. And after if we have heated further like 200 degrees centigrade, there will be further more formation of serrations. But if we have increased it to 300 degrees centigrade, or let's say up to 573 Kelvin, and then there is a sufficient temperature for metal to plastically deform, so there will not be any formation of serrations. So we can see that there is a significant increase in ductility and decrease in the strength of the material. So this is called Portevin-Le effect. Now, why yield point phenomena is prominent in low carbon steels, while in high carbon steels this is absent. So this is a very important question. In low carbon steels, atoms are dissolved in the matrix as interstitials, which are known to expand lattice around them. Dislocations create tensile stresses below the positive half as dislocation. Therefore, highly mobile carbon atoms readily occupy these positions near dislocation core. The binding energy of carbon with dislocation is about 0.5 electron volt. So pinning of dislocation on carbon atoms trapped in the dislocation core explains high yield stress, which rapidly drops down to Pulse-Navarro stress when the dislocation is released. In high carbon steels, carbon segregates and forms carbides. Therefore, its concentration in the matrix reduces. Its concentration means carbon concentration in the matrix reduces, and carbon will not be available for pinning of the dislocation. So that's why no yield point phenomena is observed. Now, why yield point phenomena is not observed in dual phase steel? Dual phase steel means ferrite and martensite. So as we know that when in the dual phase steel there is transformation from austenite to martensite, and there could be some retained austenite also. So if we refer to dual phase steel, then we have a ferrite and martensite structure. So there are two reasons why we don't observe yield point phenomena. First is that due to transformation of austenite to martensite, an excess of dislocations are generated in neighboring ferrite grains which are not trapped by carbon atoms. Therefore, material has sufficient mobile dislocation density during the onset of plastic deformation. The transformation of austenite to martensite causes increase in volume, which produces a strain, and the strain is accommodated by ferrite, and adjoining area is plastically deformed, and the dislocation density and hardness increases. Once there are a lot of dislocations, total atmosphere is not effective. Or otherwise, we can say that if we have a very high dislocation density, then this yield point phenomena explanation is not valid. Because once there are lot of dislocations, quartal atmosphere will not be effective and it cannot hold dislocations, and hence no yield point phenomena is observed. Second, during traditional processing, intercritical annealing of these materials, the majority of carbon is redistributed into prior austenite. Afterwards, what usually follows is galvanizing process. At that point, carbon in ferrite is reaching an equilibrium value either by precipitation or redistribution. Hence, there is not significant supersaturation of carbon in ferrite, and carbon that is responsible for trapping of dislocation. In lab setting, galvanizing step won't be there. So in that case, you just quench the material after intercritical annealing, and if you store at room temperature, after some weeks, you could also observe some minor signs of yield point phenomena. But generally, in industrially processed dual phase steel, there won't be any yield point phenomena. Why yield point phenomena is not observed in interstitial free steels? This is also very interesting question. What do you mean by interstitial free steels? That means it has almost no carbon or nitrogen interstitial atoms. So if you observe yield point in such a steel, it would be due to the following reason. Not sufficient Ti and niobium has been added to bind carbon and nitrogen atom. But in industrial processed interstitial free atom in interstitial free steel, carbon is 0.027% and titanium and niobium is about 0.02%. So there is no free interstitial carbon due to low carbon and nitrogen, and quartal atmosphere is not observed. Hence, no yield point phenomena in interstitial free steel is observed. But if it is observed, then it may be that there is a little bit of carbon. So this is the thing. Now this is a question on stress strain curve. So we have four stress strain curve, and correspondingly we have four materials. So this P corresponds to mild stress, as we have discussed in most of the our presentation, and Q corresponds to copper, because in copper we don't have any yield point phenomena. So high purity copper we have stress strain curve uh, like this, and in R we can see there is a brittle fracture. So brittle fracture, in which case we will have a brittle fracture, that is in glass. So R is corresponding to 4. And here we have sharp increase in the length, and this will be in the case of polyester. So C is the correct answer. Now we discuss a numerical for a bronze alloy. The stress at which deformation begins is 275 megapascal, and the modulus of elasticity is 115 gigapascal. What is the maximum load that may be applied to a specimen with a cross-sectional area of 325 millimeter square without plastic deformation. Second part of this question is, if the original specimen length is 115 millimeter, what is the maximum length to which it may be stretched without causing plastic deformation? So we need to determine the maximum load that can be applied without plastic deformation. So we need to determine Fy, yielding load, is equal to sigma y a0. So it comes out to be 89,375 Newton. And the maximum length to which a sample may be deformed without plastic deformation is determined from epsilon is equal to L final minus L initial divided by L initial, or delta L upon L0, and epsilon is equal to sigma upon E. So we can write L final is equal to L initial 1 plus sigma upon E. This comes out to be 115.28 millimeter, or delta L we can calculate to be 0.28 millimeter. Thank you for your attention.